Okay, good morning to everyone. So here, today's class I am going to discuss about the junction capacitances and breakdown mechanism. Okay, so myself, B. Krishna, Assistant Professor, Department of ECE. Okay, so now here I am going to discuss about junction capacitances. So here, let us see here. It is the PN junction diode. As I told you previously, I discussed about this PN junction diode. This is nothing but P-type material. This is nothing but N-type material. So by doping these P-type impurities in half of the diode, half of the crystal material, and doping the N-type materials on the another half of the crystal of this particular silicon material, then the P-type device, N-type, P and N-type, nothing but PN junction diode is formed. So here, whereas coming to the P-type region, there are majority are holes, minority are electrons, but not shown here. And coming to the N side, here the majority are electrons, minority are holes, but such are not shown here. So here, this is nothing but depletion region. The width of the depletion region is nothing but denoted with W. And here junction, it is J, represented with J. As you know about this, already discussed in last classes, what is the functioning of P-N junction diode after doping the concentration of impurities to P side and N side. We are discussing several operations like open circuited PN junction diode and short circuited PN junction diode, and that is forward bias condition and reverse bias conditions. Based on that, also there we are observing the characteristics of the PN junction diode. But now here I am going to discuss about the junction capacitance. So here junction capacitance means there in junction it has some property, that property nothing but here he says it is capacitance property, that is junction capacitance property. So here this junction capacitance property will be depending upon the type of the conditions of the diode. So conditions means, as I told you in previous class, there are two types of biasing conditions, such as nothing but forward bias condition and reverse bias condition here. So here let us see the first point here. Depending upon the biasing conditions, such as biasing condition nothing but forward bias condition and reverse bias condition. The two types of capacitance are existing in this diode, such as I think first one is transition capacitance and second one is diffusion capacitance. Okay, let us come to the transition capacitance. So here the diode is going to the reverse bias condition. So this is the reverse bias condition here we are applying. Here holes are nothing but positively charged area here more. And coming to the N region, here negatively charged particles are more. Here for negatively charged area we are making connection with the positive terminal, and coming to the positive charge area we are making the connection with the negative terminal. So then what happened? Already you know about that concept, because of you already know about the concept. Such is nothing that is nothing but here the major charge particles are holes. Those are moving towards this negative charge or negative terminal area, and here major charge particles are electrons that are looking towards the positive charge terminal. Then what happened here? The majority charge particles are moving away from the junction. So here, so this positive charge area nothing but that is plate 1, and here it is nothing but N-type region is nothing but act as plate 2. In between there is a depletion region. The depletion region, here it is a dielectric medium is here there. Okay, and here first point, under the reverse bias condition, PN junction diode in figure is shown here. The majority charge carriers are moved away from the junction. The majority charge carriers, here the majority charge carriers are moved away from the junction. Okay, here the majority charge carriers are moved away from the junction. Away from the junction means they are moving from away from the junction towards this direction and towards this direction, then automatically the depletion region will be increases. As in this case, the width of the depletion region and the width of the depletion will be increases by increasing the reverse bias voltage here. Okay, by increasing this reverse bias voltage, large number of charged particles such as major charged particles are moving away from the junction. Then automatically the junction is increases. Nothing but the depletion region will be increases. So here initially we are applying here a 0 volts at this DC supply. Initially we are applying 0 volts, then they are having some carrier concentration in the N region and P region such as major charge particles. By increasing this voltage, then what happens, they are moving towards this direction away from the junction. Then there is a change in pole density, change in current density with respect to applied voltage. Okay, what's that? If you are applying, if you are increasing this voltage, increasing this voltage here, or varying this voltage here, then there is a change in pole density or change in electron density will be occur with respect to this applied voltage. So that change in pole density or change in electron density here we are saying here it is here today. So the change in charge, that is the finally we are saying that is the change in charge with respect to applied voltage. The change in charge nothing but dq. Here q nothing but that it is a charge carrier. We can represent with the charge. So the change in charge with respect to the applied voltage, that is dV. dV nothing but change in voltage also. Okay, as I told you here in this slide. So here initially we are applying input voltage here it is DC supply voltage, external voltage nothing but 0 volts. Then it will slowly varying, nothing but change in voltage. Automatically the charge carrier concentration such as major charge carriers in these regions also changes. Is nothing but change in charge with respect to change in voltage. So here he says that as dq nothing but change in charge with respect to this applied voltage. So this change in charge occurs with respect to this applied voltage. Nothing but capacitive effect is exist. Okay. So such capacitance which comes into the picture under the reverse bias condition is called as transition capacitance. Transition means just transist one, they are transfer from one point to another point. Nothing but initial point to final point. Okay. It is nothing but transition capacitance. That transition capacitance will be exist at this particular junction. So here, if the magnitude of the capacitance CT is given by this equation, CT equal to dq by dV. So transition capacitance nothing but that is transition means changing the position, one point to another point. Nothing but here the charge carriers are changing the position. They are moving away from the junction towards the positive charge area, towards the positive terminal such as electrons, and the holes are moving towards the negative terminal in P side. That is the change in position of the charge particles. That is nothing but transition capacitance. That change in charge is occur due to this change in voltage. Okay. Next, this capacitance is very important here as it is not constant. Okay, when the change in charge occurs with respect to the change in voltage, there is a capacitance property exists across the junction, but it is not constant. Why? Because he is saying it is not constant. If you are applying this voltage, increase again, you can increase that reverse bias voltage, then automatically the capacitance property will be decreases. Why? Because the depletion region will be increases, the existing electric field also decreases. Due to that, the capacitance property also decreases because of the depletion region will be increases. Suppose the depletion will be decreasing position, there are higher carrier constant, there is high electric field intensity available at the junction. But here, due to the reverse bias condition, the depletion region will be increases due to that. So here, the capacitance property also decreases. That will be shown in the next slide. That is a graphical point of view. Okay. This is this capacitance is very important here as it is not constant but depends on the magnitude of the reverse bias. Okay, here this one says the capacitance is not a constant, but it is depends on the magnitude of the reverse bias voltage or reverse voltage. Okay, so here W is the width of the depletion region. Then the transition capacitance is given by CT equal to epsilon A by W. So here change in charge across this junction nothing but here epsilon is nothing but permittivity of the semiconductor and A is the area of the cross section. So here the permittivity of the semiconductor is shown here nothing but another parameters epsilon naught and epsilon r. Here epsilon naught is nothing but permittivity of the free space and here epsilon r is relative permittivity. So finally we are taking this value epsilon is nothing but equal to 8.84924 of minus 12 farad per meters. So let us go this capacitance property shown in a graphical point of view here. Let us see here. As the reverse bias voltage here applied to the junction increases, as the reverse bias voltage applied to the junction is increases, then the width of the depletion region is increases. As I told you in previous slide, as you are applied reverse bias voltage is increasing order, then the large number of charge carriers such as holes or electrons are moving away from the junction, then automatically the depletion region will be increases. Okay, as shown here, let us go to the diagram here. So this depletion region will be increased. Why? Because again we are increasing this biasing voltage here, then automatically the major charge particles are here whole. They are largely moving towards the direction. Here electrons are large amount of here. That large amount of electrons are moving towards the direction. Then automatically the depletion region will be increases. Okay. So here, okay, thus the transition capacitance CT will be decreases. So the capacitance can be controlled by the applied voltage. Okay, so this capacitance is controlled by the applied voltage. The variations of the capacitance with respect to applied reverse voltage. That variations occur due to the applied reverse voltage. So this capacitance varies from 80 picofarads to less than the 5 picofarads as VR changes. VR nothing but reverse bias voltage changes from 2 volts to 15 volts like this. So let us see this diagram here, graphical point of view here. So this is the capacitance is taken in a y-axis in picofarads, and the voltage taken here it has a reverse bias voltage in x-axis. Let us observe the diagram here. So initially we are applying input is 0 volts like this here. Then it is maximum capacitance occupies across the junction. So this is the transition capacitance like this. This curve is nothing but transition capacitance curve. Okay. So let us see here. Here the reverse bias voltage 0 volts. Then what is the capacitance here? The maximum capacitance here. Suppose the reverse bias voltage in increasing order means then automatically the capacitance property will be decreases like this. Okay. So let us see this point again. As the reverse bias voltage is applied to the junction is increases. So this is the reverse bias voltage here. Then the width of the depletion will be increases. Thus the transition capacitance CT decreases. Okay, so all those things you have to observe here. Here 0 volts is not 0 volts initially, maximum capacitance here. By increasing this voltage, the capacitance property will be decreases. Okay, this is nothing but the transition capacitance of the particular PN junction diode. Next, go for the diffusion capacitance. So during the forward bias condition, another capacitance comes into the existence called diffusion capacitance or storage capacitance denoted as CD. So in forward bias condition, let us see here. In previous case, there are we are applying reverse bias to the particular diode. Then the depletion region will be there. The depletion region is increasing order. But here it is for P type. The P type, the majority are holes. That is nothing but positive charge ends. So for P type, we are making here connection as a positive terminal. Here the majority are electrons, which are negatively charged particle. For negative charge per area, we are making here connection with the negative terminal. This is nothing but forward bias voltage, the battery. So what happened here? When we are applying positive charge particle for the positive terminal for the positive charge area, then they are repulsed into each other. Then they are moving towards this junction like this. Then they are moving towards the junction. Similarly, here major charge particles are electron. Those are negatively charged area. Therefore, negatively charged particle, we are applying negative terminal. Again, they are repulsing to each other. Then they are moving toward this junction. Then what happens? Automatically, the depletion region will be decreases. Okay, depletion will be increases. So how this depletion is formed? As I told you in previous classes, already know that basic concept of this particular junction due to the concentration gradient. Okay, so let us see these points here. For during the forward bias condition, another capacitance comes into the existence called diffusion capacitance or storage capacitance denoted as CD. So in forward bias condition, the width of the depletion region decreases and holes from P side gets diffused into N side. So here the holes are diffused into P side, gets diffused into P side, like the electrons are diffused gets from N side to P side. Okay. Here, while the electrons are moved from N side to P side as the applied increasing concentration of injected charge carrier. As the applied voltage here, increase the concentration of injected charge carriers that are increases. So then the rate of change of injected charge carrier with applied voltage, nothing but defined as diffusion capacitance CD. That is opposite for the particular transition capacitance concept. This is the opposite concept. Because of here we are applying positive voltage, there we are applying reverse bias, here we are applying forward bias. Okay, here the now the capacitor property is very high here because of it is the area of this particular junction is less because of we are applying here it is a forward bias condition. See here, the different capacitance change in a charge carrier is nothing but there exists a one capacitance property that is nothing but diffusion capacitance. That here CD equal to dq by dV. As you know here, change in charge with respect to change in voltage. Okay, the diffusion capacitance can be determined by the another expression that is CD equal to tau into I current by eta Vt, where tau is the mean lifetime of the holes. Okay, so the diffusion capacitance is proportional to the current. The diffusion capacitance is proportional to the current. Proportional to the current, the diffusion capacitance here is increasing order. Why here it is increasing order? Because of the depletion region area will be very less. So there exists a electric field intensity due to that less area. The capacitance property is also in increasing order. How it is increasing order? By applying the forward bias condition. As I told you in previous classes, when the diode is a forward bias condition, then we are expecting the current is generated. Okay, the current is generated nothing but when we are applying forward bias condition to the particular diode, the current will be generated in increasing order as we are varying the forward bias voltage. So like here also, the diffusion capacitance is proportional to the current. The capacitance is nothing but it is proportional to the current. So in forward bias condition, let us see next point here. In forward bias condition, the value of CD is the order of the nano to microfarads. But in transition capacitance, it is in picofarads. Let us compare these two. Here nano to micro nothing but here it is the picofarad. So compared to these two, this is the very more or much more compared to this particular picofarads. So it is greater value compared to this pico value. It is nano mean 10 to the power of minus 9 to 10 to the power of minus 6. But here 10 to the power of minus 12. It is very less amount of value compared to this diffusion capacitance value. So the diffusion capacitance is much greater than the transition capacitance, that is CD is very greater than CT. Okay. However, here in forward bias condition, diffusion capacitance is appears in parallel with the resistance. Okay, so let us see here in a graphical point of view. By increasing the forward bias voltage, here generally in forward bias condition we are taking the current on y-axis, voltage on x-axis. By increasing the forward bias voltage, then the current is also in increasing order. Like this, here the capacitance is also in increasing order. That's why he says here in this point. So the diffusion capacitance is proportional to the current. By increasing the forward bias voltage, the capacitance will be in increasing order. So this is nothing but forward bias condition. So this is the graphical representation of the diffusion capacitance of particular junction diode, junction capacitance of the diode. Next, so here we are going to discuss about the breakdown mechanism in diode. Breakdown means, so generally this breakdown will be occurs in the reverse bias condition. So breakdown means certain amount of reverse bias where we are applying a reverse bias voltage. That reverse bias voltage will be having some point. That point will be suppose the input voltage exceeds that point, then automatically the breakdown will be occurs in this particular diode. Okay, so here let us observe this particular graph here. So this is the nothing but forward bias condition. This is forward bias. Okay, and this is nothing but reverse bias. Already we seen in a particular PN instituted characteristics here. Like this here also can draw here. This is the forward bias condition. This is the forward bias condition, and this is the reverse bias region. This is the forward bias region. In forward bias region, you are increasing the input voltage here, then automatically the current will be increases like this. Up to this level, this is the cut-in voltage or cut-off voltage. So this is silicon. For silicon, it is like 0.6 or 0.7. Okay, so up to this, we are not expecting any voltage. Why? Because it is a minimum range. we are applying input voltage, that minimum range will be exceeding, then only the diode will be going to conducting mode only. If the diode is in conducting mode, as well as your applied voltage will be in increasing order, then the diode will be going to in operating condition. Then we are expecting the current is in increasing order by increasing the voltage. Similarly, coming to the reverse bias condition, so here diode is simply it act as a open circuit, or simply it is a half, like it is a half condition, a switch off like that. So generally we are not expecting any current, but simply you say if the diode is in a reverse bias condition, is there any current? If anyone asks you, then simply you say there is no current. That's not correct answer actually. But there is a current is exists. That current is nothing but reverse current. Reverse saturation current means that current is existed due to the minority charge carrier current. Minority charge carrier current. Okay. So this reverse bias condition is for majority charge carrier in the P type and N type semiconductor material. But in their P type, such as holes, such as majority, but in that P type material also minority charge carriers also available. So let us go to that particular PN junction right here. Like see here, here majority charge particles are holes. Here we are applying positive. Okay. Here minority are nothing but electrons here. So if you are applying reverse bias condition. So then here reverse means here we are applying negative voltage. It is negative charge particle such as minority charge carriers. Then they are accelerating to each other. Then automatically they are moving towards this junction. Similarly, here we are applying positive. For example, here holes are minority charge carriers. For minority, nothing but it has a positive charge, and for positive charge, and you are applying positive terminal, then automatically they are looking toward this junction. So, due to this movement of minority charge carrier current, we are expecting there is a current that is nothing but a reverse saturation current, but it is not considered practically because of it is very less amount of current is existing in this particular junction when we are applying reverse bias condition. Okay, that's why everyone says simply, sir, there is no current, but there is a current. Okay, that current nothing but reverse saturation current up to this level. This is the reverse saturation current represented with the I naught. Okay, right. So coming to this point here, first point, consider the diode characteristics in reverse bias condition as long as reverse voltage is less. Reverse voltage is less than the breakdown voltage. So here we can mention this point is nothing but VBR. V nothing but voltage, B nothing but breakdown in reverse bias condition. VBR nothing but breakdown voltage region. If your applied voltage exceeding this level, then the breakdown will be occurs. Automatically the current will suddenly increases. It may be damaging the particular PN junction diode. So that problem will be overcome in the next concept, that is the another concept. So okay, here consider the diode characteristics in reverse bias condition as long as the reverse voltage is less than the breakdown voltage and the diode current is small. Diode current is very small. So this is the small current like this here. Very less amount of current is generated. And almost it is constant also. Almost it is constant, not increasing order. Up to this level is not in increasing order. It is maintaining a constant at I naught. So when second point, when the reverse bias voltage in increasing beyond the certain value, so this reverse bias voltage VR, this is the VR is going to like this here. So beyond this value, then what happened here? Let us see here. Beyond the certain value, then the large diode current flows. This is the current here. Large current is flows in this way. Okay. So this is called breakdown of the diode, and corresponding voltage is called reverse breakdown voltage, that is VBR of the diode. However, there are two distinct mechanisms due to which the breakdown may occur in the diode. Okay, there are two mechanisms. So here breakdown mechanism nothing but What is my breakdown here? We are discussing here, but based on that, here we are going to discuss about the two breakdown will be occur in this particular diodes. Diode, nothing but avalanche breakdown diode and Zener breakdown diode. Here, as you when you go through this particular avalanche breakdown and Zener breakdown, like those are similar properties, but there is a slight difference. That slight difference you have to observe. Then only it is easy for you. Otherwise, there is a slight confusion also. Okay, so let us go to the avalanche breakdown. Okay, so this is the avalanche breakdown here. Let us see, this is the one of the atom here, this is one of the another atom here. Before going to that, here, let us see here, this is a high velocity change charge carrier and original charge carrier and dislodged charge carrier, and they are releasing a number of electrons here. Initially, there is a one charge particle moving like this, and it is going to some operation here, and then it is going to release just some other charge particles. So like 1 into 2, and the two are again going to like this place. That is another concept here. I told you. Then again it is releases two charge particles, and this is one also releases two charge particles. Finally, 2 into 4. So this is the total 4 charge particles are available here. In next concept, 2 into 4 means these two. This one is releasing 2 charge particles. This one is releasing 2 charge particles, and this one is releasing 2 charge particles. This one is releasing 2 charge particles. It is 8. So initially it is 1, but finally it is going to 4. So means what we are observing here, the number of charge particles are increasing. The number of charge particles are increasing order. How such charge particles are increasing order? In previous case, the breakdown will be occurs due to increasing the minority charge carriers, where again we will go through this particular graphical point here. Okay, here up to this, no problem. There is a current, that is slight amount of current. If it maintains a constant value, it is not observable. So it is very less amount of current. So it is reverse bias current. But up to the when we are input voltage, that is reverse voltage, will be exceeding this level, then the current will suddenly increases. How it is increases suddenly? Because of the minority charge carriers are increasing suddenly. Increasing suddenly. So here this current is nothing but minority charge due to the minority charge carrier current. So up to this level, it is no problem. If you are input voltage that is in reverse bias condition exceeding this level, then minority charge carriers are increasing order, suddenly in large increasing order, then automatically they are moving towards a particular direction. So then the current will be suddenly increases. So how the minority charge carriers are large number of charge increasing to large number of charge carriers? How the charge current will be, how the current will be increasing, that will be going to discuss in this concept. Okay, first point. We know that when the diode is in reverse bias, a small reverse current is I naught flows across the junction because of the minor charge carriers in the depletion region. It's good, it's correct. Okay. Next, here the velocity of the minority charge carrier is indirectly proportional to the applied voltage. The minor charge carrier is the velocity. Here, one of the important point here, the velocity of the minority charge carrier is directly proportional to the applied voltage. If your applied voltage increases, the velocity of the charge carrier will be increases. Hence, when the reverse bias voltage is increased, the velocity of minor charge carrier will also increases, and consequently their energy content will be also increases. Energy means, suppose initially if you go anywhere to talk some others, initially so one person is going, it is having some less amount of energy to the one person side, other person there are two person like that, the one person side is very less amount of energy, so some other persons are added to there, it is energy will be increases. Like that here also, here the reverse bias voltage is increasing order, there is a atom will be there. By applying this reverse bias voltage, the minority charge carrier will be increases the velocity, it will be hitting to the atom. So this is the valence band orbit. As I told you, I think it is known in physics, still physics. So here, this is the this minority charge carrier. It is initially it is a one single charge particle, Here, high velocity charge carrier. It is high velocity charge carrier. How it is high velocity charge carrier? By increasing the reverse bias voltage, it velocity will be increases. So then it is hitting to the another atom. So here it is a covalent bond. It is. So when it is hit to this particular outermost orbit valence band charge particle, so then this outermost valence band charge particle will be releases. Okay, released. So means there is a electron hole pair will be formed. There is a electron hole pair will be formed. Once the electron will be jump from this particular area, so then a hole is there, electron will be released. So this electron and hole is nothing but electron hole pair he is called. He's saying that like that. So this electron, when the electron will be that when the minority charge carrier will be hitting speedily to this particular valence band orbit or valence band atom, then the electron will be releases. Then it is dislodged charge carrier, nothing but it is dislodging charge carrier, and this is the original here, this is the original charge carrier here. So from this we are observing two charge particles here, minor charge particles. And one more point here, again it is hitting to the another charge, another atom of the outermost orbit, and this is again it is hitting here, again it is there is a electron hole pair will be formed. Okay, then it releases a two charge particle here, it is the having two charge particle. Finally increasing order, so at that point, so these increasing order will be varying with respect to reverse bias voltage. So finally the large number of charge carriers are occurred by applying reverse bias voltage. Due to that large number of minority charge carriers, the reverse bias current will be suddenly in increasing order. Okay, so let us see. This is a carrier multiplication in avalanche. Carrier multiplication. First is initially 1, 2, and 4. This is a multiplication process, increasing order like this. Next. So when these high energy charge carriers are strike the atom, as I told you in previous slide, strike the atom within the depletion region, they cause other charge carriers to break away from their atom and join the flow of current across the junction, as shown in above figure. Okay, and second point is the additional charge carriers are generated in this way, strike other atoms and generate a new charge carrier by making them to break away from their atoms. This cumulative process is referred to as avalanche multiplication, which result in the flow of large reverse current, and this breakdown of the diode is called nothing but avalanche breakdown. Okay, coming to here, okay, this is the basic concept of particular avalanche breakdown. So initially these electrons are doesn't have any energy levels, that energy level is not much, not to break up the hitting this particular atom here, covalent bond here. So by increasing reverse bias voltage, so these minority charge particles are having some kinetic energy. So due to that energy, it will be hitting the velocity of charge particle will be increasing to in terms of velocity. They are hitting in valence band charge particle, then it is releases like this. They are in increasing order, such as minority charge carriers. So due to that minority charge carriers are large, due to that reverse current will be increases suddenly in increasing order. Okay, this shown in here in this way. This is the suddenly increasing order diagram. Okay, increasing current. So at that point here, where to the breakdown will be occurs. Breakdown means the damaging the particular device. That is nothing but avalanche breakdown. Next go for the G0 breakdown. So here this is the basic concept here. This is the basic concept. We have electric field strength. We have electric field strength at the junction, that is equal to reverse voltage by depletion region. If you are increasing the reverse voltage, the depletion is increases, the electric field strength is also increases. So here the p-type and n-type materials are, as I told you, these are the doping constant, they are formed here, and here it is nothing but heavily doped materials. The p-type and n-type are the heavily doping materials here, they are heavily doped here. So due to that, the depletion will be decreases, it is the narrow depletion layer. Okay, here the p and n-type junction is heavily doped. Due to the doping, the depletion region decreasing, it is very narrow. Okay, from the above relation, we seen that the reverse voltage is directly proportional to the electric field. Hence, a small increasing in reverse voltage produces very high intensity electric field within narrow band. So that electric field intensity is what that pull up or carrying the outermost valence electron from this particular atom. As I told you in the previous, that is avalanche breakdown. There are outermost orbit is there. In outermost orbit, there is a bond there. That is valence band charge particle. When the electrons are hitting to this particular valence band charge particle, the outermost orbit valence electron charge, that is minor charge, is nothing but releases. Like that here, the electric field intensity, that intense is nothing but high strength. That high strength will be pull up the outermost orbit charge particle in the particular atom at the junction. Let's see here. This is by increasing this voltage here, reverse bias voltage, there the electric field intensity across junction will be increases. That electric field intensity is very in increasing order. That will be pull up the like here, pull the charge particle out of the valence band. That is of the stable atom. Okay, so like see here, second point here, when the reverse bias voltage to a diode is increasing, when the reverse bias voltage to a diode is increasing, so this is the reverse bias voltage here, this is negative terminal, and this is nothing but positive terminal here. Here P type we are applying negative, here N type we are applying positive. It is reverse bias condition. Okay, when the reverse bias voltage is increasing, then the influence high intensity electric field, that influence a high electric field intensity. Such an electric field enough to pull the electron out from the valence band. As I told you before discussing about this breakdown mechanism, there is a slight difference. If if it is understand, then it is easy for you. I told you in first two, that is a mechanism concept. Here in avalanche breakdown, they are moving, hitting and releasing, they are moving, hitting and releasing. But here the electric field, the influence electric field, that is high intensity electric field pull the electron out of valence band of stable atom. Stable atom. That is another concept here. Okay. So this is not due to collision of charge carriers with atom. The collision processes occur in the avalanche breakdown, but not here. Here just pull up the charge carrier out of the outermost orbit of the atom, stable atom. So such large number of electrons within the depletion region breaks the covalent bond with the atom, and thus large reverse current flows through the diode. Such creation of free electrons by increasing this reverse bias voltage, called Zener effect, and which is different than the avalanche effect, So these minority carriers constitute a very large current, and the mechanism is called Zener breakdown mechanism. Okay. This is the overview of this particular junction capacitance of PN junction diode. There are two types of capacitance that exist based on the biasing condition, such as transition capacitance and diffusion capacitance. Also, how the transition capacitance is generated across the junction, and how the transition and diffusion capacitance is existed across the junction, and the transition capacitance is very less compared to the diffusion capacitance because of this concentration of this charge particle. And similarly, there also we are observing one of the concept is nothing but mechanism concept, that is breakdown mechanism concept. Breakdown means nothing but it is occurs in a reverse bias condition. If you are applying the reverse bias voltage in increasing order to exceed certain value, then only that will be occurs. That will be damaging to our device. So we can control that breakdown mechanism. So we go for the another device, that is nothing but a Zener diode. There we have to recover that problem. Okay, and here generally the PN junction diode, here we are observing the breakdown mechanism such as avalanche breakdown and that is nothing but what is Zener breakdown. So okay, so here the breakdowns are nothing but simply the avalanche breakdown is occurs that is nothing but up to 6 volts, like that. If you are feeding that level then only the breakdown will be occurs. Commit GNR diode, it is 5 to 6 volts of voltage needed. If you are that is the voltage. If you are exceeding that level, then also the GNR breakdown will be occurs. So this is the overview concept of this particular junction capacitance and breakdown mechanism of this particular PN junction diode. So in next class we'll go for the GNR. What is meant by GNR diode? And what are the characteristics, what are the applications of the GNR diode. So this is the overview of this particular concept. Thank you.